And welcome back as we continue our cosmic journey. Previously we had discussed Newton's three laws, but now let's go ahead and use those to help apply toward Newton's universal law of gravitation. So again, Newton's laws of motion were a very important thing that was able to be applied into astronomy. His laws of motion showed that objects at rest will stay at rest and those in motion will continue moving uniformly in a straight line unless acted upon by a force. But if you remember, the planets move in ellipses. Therefore, there has to be some force that's doing it. And this force, in this case, is gravity, which is actually bending their paths so they don't simply continue off in a straight line. Newton's insight was that Earth's gravity might extend as far as the moon and produce the force required to curve the moon's path from a straight line and keep its orbit. In fact, this was a pretty radical idea for him to propose that, gravity is something that's not simply just limited to Earth. He further hypothesized because it's not limited to Earth, there's actually a general force of attraction between all material bodies. And if so, the attractive force between the Sun and each of the planets could be what actually is keeping them in their orbits. So that this idea of gravitational attraction is something that can happen between any two objects. And the rule that we can use here is we can say F of gravity is equal to G, m1 times m2 divided by r squared, where F of gravity is the gravitational force between two objects, m1 and m2 are the masses of those two objects, and r is their separation. It is this force of gravity on the surface of Earth that actually gives us our sense of weight. Mass is always going to be the same. No matter where we are in the universe, the amount of mass we have is always going to be the same. However, our weight is going to be very dependent upon the force of gravity, which is why here it's like you might weigh so much on Earth, but you're going to weigh less on the moon or less on Mars, or you weigh more on Jupiter, etc. And again, as I just mentioned, unlike your mass, which is always going to be the same no matter where in the universe, your weight is very dependent on the local force of gravity. And so, as mentioned, you're going to weigh less on Mars and the moon than Earth, even though, again, there's no change to your mass. So, what can we talk about with gravity here? Well, gravity, again, is a property of mass. Whenever there are masses in the universe, they will interact via the force of gravitational attraction. The more mass there is, the greater the force of attraction. Here on Earth, the largest concentration of mass is, of course, the planet we stand on. Earth's gravitational force is going to outweigh our own, and its pull dominates the gravitational interactions we experience. But everything with mass attracts everything else with mass anywhere in the universe. Newton's law also implies, therefore, that gravity never truly becomes zero. It's obviously going to get weaker with distance, so the farther away from something, the less influence you have. But it continues to act to some degree no matter how far away you get. So even you here on planet Earth technically could have influence on something all the way at the end of the universe. Now it's going to be permanently negligible because it's going to be very close to zero, but gravity never really stops. So that's a good question here. It doesn't really stop. What about things in space? We've sent astronauts up into space. What have they experienced with gravity? Well, if you think about it, we can ask the question, why is it that astronauts aboard the space shuttle appear to have no gravitational forces acting on them? They're floating around. They're experiencing weightlessness. Well, when they're falling, they're actually what we consider to be free fall, and they accelerate at the same rate of everything around them, which includes the spacecraft, or maybe a camera, which they're taking photographs of Earth. But because they're in this free fall state, astronauts experience no additional forces, and therefore they experience that weightlessness feeling. Again, their mass hasn't changed, but their perception of weight has. Now, technically, what's actually happening here is that the astronauts are falling around Earth, but they're not falling to Earth. As a result, they continue to be in a constant state of falling, and are said to actually then be in orbit around Earth. That's why when they're for example, the International Space Station, or wherever spacecraft they're up in, and you're orbiting the Earth, you're actually in a state of free fall because of how the gravitational forces are interacting. So that's going to kind of tie us up real nicely here for orbital motion and mass. Kepler's laws describe the orbits of objects whose motions are described by Newton's laws of motion and the law of gravity. Knowing that gravity is the force that attracts planets toward the sun, however, allowed Newton to kind of rethink Kepler's third law. So Newton's formulation introduces the additional factor of the masses of the sun and the planet, both expressed in units of the sun's mass. So here he said that a cubed is equal to m1 plus m2 times p. Now, since the mass of a planet and the sun are both nearly the same as the mass of the sun itself, Kepler, when he did his original equation, did not realize that it needed to be included. Now, if we can measure the motions of objects acting under their mutual gravity, then the formula will actually permit us to deduce their masses.